Okay, I finished up through number 8. Remember, your pictures don't have to look exactly like my pictures. That's okay. Let's talk a little more about continuity. If f and g are two continuous functions, you can add them, subtract them, multiply by a constant, multiply them, and even divide them as long as the denominator isn't 0, and still have a continuous function at a point. Let's see, so if f and g are continuous on an interval, then so are their sum, product, difference, quotient, as long as you don't have a 0 in the denominator. So, polynomials are continuous everywhere. Rational functions are continuous everywhere that they are defined. That means as long as the denominator is not 0. Now let's look at example 6. We want to know where this function is continuous. Natural log of x inverse tangent of x over x squared minus 1. So first thing I look at is the domains of each of these functions. The domain of natural log. Do you remember what the domain of natural log is? Can you take the natural log of negative stuff? No. Can you take the natural log of 0? No. So, domain of natural log is 0 to infinity. So this function couldn't possibly be continuous at negative numbers or at 0. It's only going to be continuous possibly from 0 to infinity. Where is inverse tangent continuous? Let's see. So the domain of inverse tangent. Well, what does the graph of inverse tangent look like? It looks something like that. So this one is all real numbers. And then x squared minus 1 is continuous everywhere, but since it's in the denominator, that means it cannot be equal to 0, so x squared cannot be equal to 1. So x is not allowed to be plus or minus 1. So this entire function f of x is continuous on the intersections of all these domains. So it has to be between 0 and infinity, and it can't be equal to plus or minus 1. At 0 to 1 and 1 to infinity. Now continuity allows us to calculate some more limits. So let's look at the limit as x approaches pi. Sine of x over 2 plus the cosine of x. And this is just a direct substitution problem. Sine of pi over 2 plus cosine of pi. Sine of pi is 0, 2 plus negative 1. 0 over 1 is 0. Easy peasy. Let's see. Following types of functions are continuous at every number in their domain: polynomials, rationals, roots, trig functions. Makes sense. We've been drawing those things for a long time. They have nice, smooth, pretty curves. Another way of combining continuous function is the composite function. So remember how to do the composite function. That's where you take f of g. So if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of the composite function, f of g of x, is equal to f of b. In other words, we can take this little limit here and pull it inside the function value. So let's look at example 8. We have the limit as x approaches 1, not infinity, of the arc sine of 1 minus square root of x over 1 plus 1 minus x. So we look at the limit. Actually, I'm not going to rewrite the limit there because I'm going to pull the limit inside the arc sine function. So we take the arc sine of the limit as x approaches 1 of 1 minus the square root of x over 1 plus 1 minus x. Oh, I'm determined to change that function there. Now, I'm looking at the limit as x approaches 1 of 1 minus square root of x over 1 minus x. I'm just going to look at that limit and then I'll take the arc sine in a moment. Because I am going to multiply numerator and denominator by the conjugate. And I need to write this down correctly. So I just rewrote it. 1 minus square root of x over 1 minus x. And then I multiplied by the conjugate of the numerator. That way, the limit as x approaches 1, first outer inner last, gives me 1 minus x up top. So I have the limit as x approaches 1 of 1 over 1 plus the square root of x. And that's something I can just direct substitute. So this limit is equal to the arc sine of 1/2, and the arc sine of 1/2 is pi over 6. And here's the pretty answer. So, another theorem: if G is continuous at A and F is continuous at A, then the composite function is continuous at A. Reasonable. So where are the following functions continuous? This is example 9, part A. Sine of x squared. So where is x squared continuous? Everywhere. Where is sine continuous? Everywhere. So this one is continuous everywhere. Math language for everywhere. Capital F of x, fancy, is natural log of 1 plus cosine of x. Cosine's got to have an input. So where is the inside function continuous? Well, it's continuous everywhere because cosine is continuous everywhere and 1 plus cosine is continuous everywhere. Natural log requires its input to be greater than 0. So 1 plus cosine of x has to be greater than 0, which means that cosine of x has to be greater than -1. So this function is continuous everywhere except places that cosine is equal to -1. It's never less than -1. So this is discontinuous at every odd multiple of pi. And let's see, continuous everywhere, odd multiples of pi. Alrighty, we're going to take a break here, come back, and we'll talk about the intermediate value theorem.